Welcome to Venturi Charge Motion. This is the 9th video of the New Electromagnetism video series. And New Electromagnetism is the 4th paper in the Ethereal Mechanics series. This is video EM0409. In this motion, we're going to define what Venturi Charge Motion is. We're going to derive the Venturi effects from New Electromagnetism V5. And then we're going to have some very interesting experimental discussions. So, the Venturi Charge Motion is found in section 4.4. This is for version 5.0 of the paper. There is going to be a 5.1 release, and the Plan A of the release schedule has been approved by the Patreon bridge officers and above, and the paper is going to be released in late April 2024 to Patreon members, July 4th to the public. Now, because of developments that have occurred during the making of this video, we discovered an interesting rabbit hole that is going to take us into a very interesting thing, I believe. There's definitely going to be a 5.2 release, and this will be discussed. Probably not in this video. We're going to discuss the cause of the 5.2, but not the release schedule of the 5.2 right now. So where does Venturi Charge Motion occur? Well, Venturi charge motion occurs whenever charge motion changes velocity. And just like fluid dynamics, if you're pumping current into a conductor that has a cross-sectional area A1, and that cross-section transitions down to a smaller cross-section, well, the charge will necessarily have to accelerate in this little section here. This accelerating charge is going to induce an inertial effect that can be experienced by other charges in the area. Okay, the Venturi charge motion can also cause an effect when you're transitioning from different types of conductors. Like if you're transitioning from copper to nichrome, then necessarily your charges have to speed up in order to maintain the same current. This is what's causing the anomalies. So we're going to call this the nichrome anomaly. And this is going to be shown to be related to the zinc anomaly that Tibor's brought up with the Hall effect. But we'll get to that later. In the Physics 2 software, to look at the charge motion experiments, it's under Test Charge Motion. There's a section for Centripetal. For the experiments we showed in the last video, in this video we're going to show 3 different simulations. One for a tapered Venturi effect, an abrupt junction Venturi effect, and a dissimilar metal Venturi effect. This is the tapered conductor Venturi effect. In this loop, we have 100 amps flowing around counterclockwise. Over here is a detection loop of wire. Because of the acceleration of the deceleration of the current up here, and then the acceleration of the current back down here, there's going to be a DC voltage induced in this lobe. DC, not AC, DC. Here we have the world's first DC to DC transformer, where we're putting a constant current in, and we're going to get a constant voltage out. So this is not induction. It's not any form of induction, because all the other forms of induction are time derivatives. This is a time constant. This is something nobody's ever seen before. So what this loop shows is we have 30 gauge wire here, and this is 14 gauge wire here. The sizes are exaggerated so you can see the taper. Okay, so what I'm going to do now is I'm going to insert a sensor plane between the source loop and the pickup loop, the target loop. Now what you're going to see is, because we have centripetal junctions here where the current's going around corners, where we're going around a very small conductor corner, we're going to get a very sharp, very powerful centripetal effect. Over here, where we're going around a thick wire corner, you're going to see it's not so much. So let me insert the sensor plane now. And there you go. The centripetal effects over here are tiny compared to what they are at the corner. And what I'm going to do now is, so we can focus on these little arrows, I'm going to go zoom in down here. So what we have, we can see the centripetal effects here are drawing the current in from the corner and drawing it in from the corner here as well. Okay, these arrows would normally be going straight toward the center right here, but because of the Venturi effect in this, they're being deflected at a diagonal angle. And the issue here is, because we're doing the Venturi effect over a very long tapered section, it's not really producing a lot of acceleration, so it's hard to see that effect in the light of the centripetal effects here. So the next thing we're going to show to make this effect more powerful is we're going to do the effect in one instant junction. Now again, I've made the copper wire here, this is 14 gauge and 30 gauge. I've made the wire thicker than normal, and it's just a case of it looks like it's getting fused into that. That's just because I made this bigger than it really would be. In the correct geometry, this is not touching this wire here. So just take that as a grain of salt, because it's hard to see it if it was printed the actual size. It'd be hard to see on the screen. So now that we put the entire Venturi effect into a very short junction, this 100 amps now induces 9 microvolts as opposed to the 2.6 microvolts from before. Now I'm going to insert the sensor plane so you can see the effect. And notice the much more powerful effect we get here. Now let me zoom in on this again, and you can see, because the power of the junction is a lot of power, it basically overrides any of the effects from the corners, and the arrows can go straight in the correct direction they're supposed to be. And then when we get closer to the centripetal corner, they cancel out, and then the arrows go in toward the black hole in the center. Okay, the next one, which is going to be where the stinking rabbit hole was discovered. This is the dissimilar metal junction simulation. In this one, we're going from a copper conductor, a 14 gauge, into a nichrome conductor, also 14 gauge, 100 amps. And you'll notice that we have 14.5 nanovolts coupled into our pickup loop here. And that's DC, of course, but this is interesting because that's a lot smaller than I would expect, considering that nichrome has 100 times the resistance of copper. I would expect something much, much, much bigger than we get with the centripetal effects. But now the more interesting thing happens when I insert the sensor plane between the junction and the pickup plane and zoom in. And look at this. The arrows are going in the wrong direction. And this is what I'm calling the nichrome anomaly. Because one thing I've noticed is that the published values for nichrome are off. They don't make any sense. For example, if you go online, they're going to say that rho, which is the ohms per meter, or the ohm meters of nichrome, is 1.1 times 10 to the minus 6 ohms per meter. Ohm meters. This is rho, okay? This isn't a resistance. You have to multiply this by the cross-sectional area and then divide by the length. And this gives you the resistance of your conductor. It's a lookup value. Okay, the published value from the manufacturer, and this is for 8020 nichrome, they publish it to be 1675 as 1.6 as opposed to 1.1. Big difference. Okay, now what I've done is I put it into the spreadsheet. I know the spreadsheet's an eye chart, but let me just present on top of this what I'm trying to get across here. So what this chart shows is that if you have any two of the components, you can compute the third. In the first case, I put in the measured value for rho, and I put in the measured value for the number of mobile carriers, and this is the number of mobile carriers per unit volume, and this is 9 times 10 to the 28. And then from those, if I try to compute the mobility, I get 4.1 times 10 to the minus 5. Well, that's way off from the published value of 7. In this case here, I put in the rho value, and then I put in the published value for mobility, and I try to compute the number of mobile carriers per unit volume, and I get 5.3 times 10 to the 28 carriers per cubic meter, which is about half, way off. Substandard. And likewise, when I put in the number of mobile carriers and the mobility, and I compute the resistance, I get a value that's way off the actual measured value. So this is what I'm calling the nichrome anomaly. Nothing fits. And because the bigger problem is we use this value in the computation in the physics software. And let me bring up the copper values. This is the value that's used for copper right now. This is the value I put in for nichrome. As you can see, it looks like nichrome has more mobile carriers per unit volume than copper. And that is why the arrows come up backward. And because these values are almost identical, that's why the value came up down in the nanovolts. Which means, and this was that what we're doing here isn't right. This may work for conductors, but it doesn't work for all metals. We have more to go here. Okay, now one of the things that, well, you would think that if you're pushing current through a two-wire junction, that if the resistance of one wire, this should be 100, times the resistance of the other wire, that the current would have to move 100 times faster. Okay, that number should be 100. Okay, velocity should be proportional to resistance, or velocity should have something to do with resistance. And then I scratch my head and I go, let's take a look at this. This is new material. I never really looked at the units of resistance before, but let's look at the units of resistance using the legacy units of resistance. Remember, the blue dye means, the blue ink means this is legacy values, legacy units. So legacy resistance is taking legacy voltage and divided by current. Okay, voltage is joules per coulomb, and current is coulomb per second. Because this is the denominator, we multiply seconds over coulomb. That's the equivalent of dividing by current. Now take your seconds per coulomb squared, move them over, and let's expand J into its values. The joule is kilogram meter squared per second squared. Now we resolve and cancel all the things, and we end up with that the units of resistance are kilogram meter per second per coulomb squared. Basically a meaningless mumbo-jumbo of units that tells us absolutely nothing about what's going on. It's completely arbitrary, useless, worthless. So now, let's see what we get when we look at resistance in terms of natural units. Okay, I'm not going to go through this for you, but the last end result here is that resistance resolves to meters per second, which is velocity. Exactly what we should be considering that resistance should be related to velocity. In fact, its units are velocity. Okay, so this is an eye-opener. I never really looked at the units before, but this experiment has forced me to actually look at it. And this is new material that's included in the 5.1 version of the paper. So again, resistance in the legacy unit is completely meaningless gibberish. In natural units, it is very meaningful and correlates to what we should think resistance should be correlated to, velocity. If you have a higher resistance, there should be higher velocity somewhere. Okay, but right now our job now is to find out how this correlates to underlying mechanisms in material. Okay, that's maybe another paper. Right now we need to find a means to get the 5.1 and the 5.2 paper published and off, and then we can look at this later in more detail. But right now, if I put a more meaningful value in the physics software and I replace the mobile carriers of nichrome with, instead of the value they got, a value that's 100 times less mobile carriers, well, I end up getting a meaningful value at the junction, which is underneath the sensor plane here, and the arrows are going in the right direction this time. Makes you go, So, what does this all mean? It means that we are using this construct here, this charge per meters cubed per volume here, We're using it. We used it in the Venturi. We're using it for the dissimilar metal, and we're also using it for the Centripetal Venturi. And we're also using it in the Hall derivations, which is a later video, but I've shown in one of the status videos already that we get the exact same equation for the Hall effect that they do with classical theory. Okay, and that's one of the things that gave me the go-ahead that this is the right way to go. But now I'm thinking, oh, wow, well, yeah, we followed classical theory and we got our ass in a sling. Okay, so now Tibor, this is interesting because this may dovetail with the other anomaly, the zinc anomaly I'm calling it, where they measured a Hall effect and the voltage is backwards. This, remember, we got the arrows backwards by having the wrong values for nichrome. And they, according to the measurement made by the researchers, zinc has its Hall voltages backwards. Now, there's a lot of other things going on because zinc and copper, also known as how you make a battery, there could be other things going on, but I think this is going to all resolve together. So I think the zinc anomaly and the nichrome anomaly are going to be two halves of the same coin as we go forward. So this is going to require some precision experimentation. Okay, and there goes my summer vacation. I was hoping to use a summer vacation to kick off the cosmology, you know, get new electromagnetism V5 behind me and kick off cosmology. But we have to nail this down. And depending on how this works out, it could just be a case that the published values are wrong, and we just have to get those fixed and get the right published values. That's going to be the easy way out. The hard way out is this is going to have to all new physics here. But it's only going to affect this part of these equations. The geometry and everything else of the derivations in the paper are going to be fine except for a revision here. And the 5.2 revision, if it's going to happen, is just going to be a change to these equations here. Okay, so that's why I'm going to continue the release of the videos, because all it's going to mean to me is producing an errata for the paper now that we know where to look here. Okay, so what I'm going to do now, I'm going to continue the Venturi equations with the knowledge that one of the factors that are used in the equation are possibly going to change when we resolve the zinc and the nichrome anomaly. So in the paper, we consider that current going through a channel of a particular area is going to get scrunched down and it's going to move faster when it goes into this smaller cross-sectional area. But what we've done for the centripetal stuff is we made it easier on ourselves by setting the length of this junction to 0. And we're going to do that here as well and turn this from a tapered form into what we're going to call a junction form, an abrupt change. Okay, and that's going to make life a lot easier because that means in between two sections of wire that change area, all we're going to do is insert a little impulse thing in the software that says this change is going to cause a a Venturi inertial effect that's going to spread out and affect other charges. Very easy to do. Okay, then if we ever want to do a tapered kind of thing, all we'll do is just slap a whole bunch of successively smaller wire areas together to simulate the junction that we want to simulate. In fact, this is done in the tapered section example in the physics software. If we blow up this tapered section of wire, you can actually see the little scallops of each disc as they get smaller. In between each one of these discs, there is a software that impulse implanted that is emitting the effect from this change as it goes. Okay, so being able to do this as a Venturi junction is a lot easier for the software simulation and all that stuff. Okay, and these are the junction equations when you set the length of the junction equal to 0. Again, the QM3 are going to be the parts that are going to change when the nichrome anomaly is resolved, or could change if the nichrome anomaly is resolved. It could just be that we have mispublished values for QM3 for nichrome. Okay, that's going to be the easy way out. The hard way out is going to be new physics. And so this effect is emitted at the junction between these two wires here. Now, if you recall, we did the same junction effect for the centripetal video the last time. In the junction where two wire segments come together and they transition from one direction to the other, Again, we insert a software impulse in here that accounts for the change in charge direction. And this is how you account for that based on the insertion angle and the exit angle of the charge. And again, we're using that same charge per mobile carriers per unit volume. This is a derivative of the mobile carriers per unit volume. This is a mobile carriers per unit volume multiplied by the cross-sectional area of the wire. This will change too when the nichrome anomaly is resolved. So, why can't we unify this with the Venturi stuff? So all we'd have to do then is instead of not just having the angle, but also having a change in size. And then we can go one step further, not just having a change in size, but a change in material. And this is how we can unify everything together. And again, these are the equations now for the unified centripetal Venturi hybrid junction. We use this now in the physics software for every change in conductor, whether it be the direction of the conductor, the material of the conductor, or the size of the conductor. And these are the unified equations for all of that. Again, these are the parts that are going to change when the nichrome anomaly / zinc anomaly are resolved. So now the interesting part of this conclusion is I wrote this first part here before I came across the anomaly. And this is very, very funny because it says, oh, we have a very satisfying unified solution for Venturi centripetal and dissimilar conductors, but there's a problem. It was too easy. Very easy implementation of the software. The Coriolis was difficult. And like I was saying to myself when I wrote this, it's just too nice. There should be a rule of acquisition against this. And so I'm saying there has to be a problem somewhere because it was too easy. And sure enough, when I finally got done with the simulations for this video, it erupted and I forgot to update this. But that's the way the problem, this is the conclusion that was going to be there before I found the anomaly. Okay, so now before we can claim success on this, we have to resolve the nichrome anomaly, which will ultimately, I believe, segue to the zinc anomaly. Okay, now we're going to work this into the upcoming electrogravity experiment. Okay, the outcome is probably going to result in a 5.2 revision. This will occur somewhere around summertime because we're going to run the experiments late June, early July over my summer break. I'm going to try to start building the experiments this coming weekend. Maybe I'll get lucky and get them done quick. Who knows? Okay, so the two main experiments that we're looking forward to are going to be marketed to everybody as the electroinertial experiment. This is how it was originally going to be done. We're going to have a pickup wire at the corner of a 30 gauge copper wire, and we're going to push 100 amps through it, pulsed, of course. Now this 100 amps is going to, so 100 amps in here is going to produce a constant 10 microvolts. Okay, and now granted it's going to be a pulsed 10 microvolts because that's going to be pulsed, but unlike what would normally happen when you have two loops coupling to each other, you would have a time derivative of this pulse would be induced in here. In this case, if I'm right, it's going to be a non-time derivative coupling here, a non-time derivative coupling. So as the amperage here goes up, the voltage here is going to go up. As the amperage here goes down, the voltage here is going to go down. If the amperage here stays constant, the voltage here will stay constant. It's a DC to DC coupling. This would be the corner Venturi effect. Okay, because we're also going to do this with the nichrome wire. We're going to do 14 gauge nichrome, 100 amps. According to physics, that should be, well, I've picked a value that I believe is fair for nichrome. We'll find out about this. That's going to give us 25 microvolts, which is within the realm of measurability at the corner of a nichrome square loop. So now these two experiments, depending on what we get, are going to probably lead to many variants based on what we learned from the initial two. Now hopefully these experiments will teach us that the nichrome anomaly is just a case of incorrect published values. Otherwise, this is going to be a mega rabbit hole potential. We'll see. The only thing we can do is see what we see. All right, so the new videos in the NEV5 series, I'm going to put this guy on hold. The conductor, I might put it on hold because, again, the results of this are going to depend on what we come up with the nichrome anomaly and the zinc anomaly. Okay, the nichrome anomaly is not going to affect the model of magnets. It will affect the Hall effect, but what we're going to beg off on here is we got the same answer the classical theory did, and then we're going to make a segue to that and say, hey, you know what? There's an anomaly that we have found, and that might affect our understanding of Hall effect for everybody. And we'll still do the conclusion look ahead in spite of the nichrome anomaly. When the videos are made public, they're going to be made public on the Ethereal Mechanics YouTube site. There'll be no more postings on the Distinti YouTube site because that is for legacy older videos, and I don't want to confuse the new stuff with the old stuff. So if you happen to see this video and you're still subscribed to the Distinti YouTube site, please subscribe to the Ethereal Mechanics YouTube site. This is the distinti.com. This is the main repository. When the papers are made public, you will find it under this link here. Also, there will be a link to the videos on the YouTube site so you can click on them and watch them in order without having to go through all of the YouTube stuff. This is the etherealmechanics.info. This is our blog site. This is run by supporters. Big shout out to Sebastian. Thank you very much. Again, when I get through everything and I get to a resting point, I will definitely get time to spend more time on here. If you want to be a big supporter of this, there's Patreon, Ethereal Mechanics. I appreciate them tremendously. Their support, they're knocking me over the head when I make mistakes. Hey, I'm human, I make mistakes. You only can learn by making mistakes. Failure is the fastest way forward. And a little heads up to the new rules of acquisition. This is the 8th rule of acquisition, the anomaly tell. Anomalies are the seeds that can grow into great oaks from whose branches we can see further. And behold, the smallest anomaly can be the harbinger of catastrophic change. And it's interesting that mainstream scientists will never admit that any of their theories or papers or publications have anomalies or counterexamples, because they're more worried about their credibility, because people are only going to pay them if people feel they're going to get the truth from them. And so you don't want to be, as a physicist, announcing, wow, yeah, your theory's got holes in it. But I swear, those anomalies are the best thing because they tell you you're not done. They tell you there's more work to go. And so that's why we have an anomaly tell. Now, anomalies are only one of 3 different counterexamples. The counterexamples include anomalies, wrong answers, and paradoxes. Okay, and this dovetails to what Niels Bohr said. He said, how wonderful that we have met with a paradox, which is a counterexample. Now we have some hope of making progress. Okay, it's not about your credibility now, because all you're going to do is stagnate science for your own selfish reasons. We have to save the human race, and that means finding the truth out about what we can and cannot do with nature. We have to move a lot of people off this planet in a very short amount of time. Okay, and sitting there worrying about your goddamn credibility isn't going to help anybody. Hold on to the anomalies, cherish them, because they are the harbingers that we have more to go. We don't know it all yet. Embrace them. So anyway, no more voodoo physics. Thank you very much.